Alright, this is a video to teach you about chi-squared tests. Now there are a couple different chi-squared tests, but this video is going to be about for a goodness of fit test, a chi-squared test for goodness of fit. So in this video you'll know all about it. Alright, so recall the process to conduct a significance test. Now I want to teach you that a chi-squared test is new, but a significance test is not new. We already know the 4 steps to conduct a significance test. Step 1 is the hypotheses. Step 2 is to check the conditions. Step 3 is the work. Remember, you got to build a model assuming the null is true. You then find your test statistic, which we've traditionally been using a z or a t-score. And then you use that z-score or t-score to calculate your p-value. And then you make a conclusion to reject or fail to reject the null based on the p-value. Well, in a chi-squared test, all of that is the same. We're going to do hypotheses. We're going to have a null and we're going to have an alternative. But this time, no symbols, all words. You'll like it. We're going to check our conditions. You still got to be a random sample. You still got to be a sample size, or I'm sorry, you still have to have a sample size that's under 10% of the population to assume independence. And you still need to be big enough. Your work is going to be probably the most different because we're not working with z-score or t-scores. We're going to work with something new. And we'll teach you about that in this video. But we are still going to calculate a p-value, so it's all going to be the same idea. And then our conclusion is once again going to be based on that p-value to either reject or fail to reject. So what exactly is a chi-squared test? Because like I said, there are a couple differences. Well, first and foremost, chi-squared tests are used for counted data of a categorical variable. No proportions in these problems, no means. So our sample data, the data we're going to look at as our evidence, is going to be counts of data for a categorical variable. Like, what's your favorite cereal? Well, Lucky Charms, Cheerios, Captain Crunch, Fruit Loops. So that's a categorical variable, and the categories are the different cereals. And the counted data comes from how many people I counted that like Cheerios. How many people did I count that like Lucky Charms? Again, so this is counted data. This is how many people fell into each category. So what you'll see here in these problems, you'll typically see a table of counts. So just imagine a table of a bunch of different flavors of cereal and a bunch of different counts of how many people like each flavor, each brand, what have you. So now there are 3 types of chi-squared tests. There's the one that we're going to focus on in this video, and that's called a chi-squared test for goodness of fit. That's what this video is all about. We also have a test for homogeneity or a test for independence. Now these last 2 are very, very, very similar, but those deal with 2 variables. Well, for this video we're going to work with 1 variable. So like 1 variable, what's your favorite flavor of cereal? Boom, that's 1 variable. Now maybe I have 7 different answers. Captain Crunch, Cheerios, Lucky Charms, Toasted Crunch, something, yada, yada, yada. But I have 1 variable. Now, the other tests that we're going to learn about later in other videos, those are for 2 variables. Like if you looked at, hey, are you in 7th grade or 6th grade? And what's your favorite flavor of cereal? So then you have multiple variables. You have gender, and then you have flavor of cereal. So again, in this video, we're only sticking with goodness of fit. So that's the most important thing, is that this is different than proportions or means because we're looking at counts. Alright, so the idea is very simple. Somebody makes a claim about what the counts of data should be across several categories. And we collect a sample to see how well those expected counts match up with the counts that we observe. And the test statistic we're going to use here is we're not going to use z, we're not going to use t. Remember, z is for proportions, t is for means. Well, we're not using proportions or means. So we're going to use chi-squared. That's why it's called a chi-squared test. Now, the Greek letter chi is written chi, but the symbol for it is this. It's an x. And it's an x with one edge is curvy and the other one is straight. So that's the Greek letter chi. And then we square it for chi-squared. So this is just like a t-score, just like a z-score. But to get your chi-squared, you do this. You take your observed counts, so how many people did I observe like Lucky Charms, minus your expected counts, how many people did I expect to like Lucky Charms? You take that difference and you square it, and you divide it all by the expected value again. So it's a very different looking formula than a z-score or a t-score. But it is just another test statistic that is not used for proportions, no p-hats here. It's not used for means, so no x-bars. It's used for counted data. Again, how many? Now, if you have, Lucky Charms, Cinnamon Toasted Crunch, and then maybe you have Cheerios, you got several different. What happens is for each category, you're going to have a chi-squared. So in each category, you're going to have an observed minus an expected squared divided by expected. And then what we do when we're all done is we add all those together. We take the sum, and that's our, our international symbol for sum, that's sigma. We're going to sum up all of our chi-squareds. Now, I totally get that that might be a little bit confusing right now, but I will explain all this in an example, and I bet it'll make a lot more sense. But the point is when you calculate your test statistic, you're not doing a z-score, you're not doing a t-score, you're going to do what's called the chi-squared score. All right, so let's kind of just dive right into an example here, and I really think through this example, it'll really kind of help. Whoa, so sorry about that. It'll really kind of help clarify things. All right, so here's an example. A vending machine typically sells an equal amount of gum for each flavor. But we wonder if that's really true. So here is what we observe from a sample of 80 purchases. So first, recognize that these are not proportions, these are not means, these are counts. I counted 25 people who bought peppermint gum, 19 who bought cinnamon, 22 who bought wintergreen, and 14 that bought spearmint. So there's only one variable. What is your favorite flavor of gum? And there are 4 different categories that you could fall into. So the claim, or not to say the claim, but we were wondering that they should be equal, right? They should all be the same. At least that's what the vending machine typically sells. But our claim is that true, or are they different? So that's the idea. I mean, boom, this is the simple idea. So we looked at a sample of 80 purchases, and this is what we observed. And we want to answer the question, are they equal, or are they really something different? So first we have our hypotheses. We have our null and our alternative. And here we're going to use words. The null would be that, nope, everything is the way it's supposed to be. Everything's what's typical, and typically they're equal. So I'm going to say the distribution of preferred flavors are equal. And the alternative would be very, very simple. The distribution, so notice there's no symbols here at all. The distribution of preferred flavors is not equal. You don't have to mention any particular flavor by name. You just have to mention the fact that they're, well, not the same. So let's, these are what we observed, right? This is what we observed of 80 purchases. And, we first have to understand what's expected, right? So I'm going to kind of make a little row underneath here called what's expected. Now, what's expected was that they were equal, right? That's what that was expected. So if you have 80 purchases, and you divide that by 4 flavors, you should be getting 20. I should have 20 people that bought peppermint. I should have 20 people that bought cinnamon. I should have 20 people that bought wintergreen. And I should have 20 people that bought spearmint. So that's the idea, right? Is that I expected 20 of each, because that's what equal means. But I saw something different. But, right, this is what I hope you understand so far of all the AP stats you've learned, is just because I see a difference doesn't necessarily mean there is a true difference, because this is just a sample. So yes, I'm not seeing these numbers match up. Cinnamon's pretty close, wintergreen's pretty close, peppermint and spearmint are a little bit off, but just because I see a difference in a sample doesn't mean there really truly is a difference. And that's why we're conducting this test, to find out, is the null correct, that the distributions are equal? Or is the alternative correct, that they really are not equal? There really is a different preference among these flavors. So I have my null, I have my alternative. Next thing I need is my conditions, right? The conditions are also fairly easy. The sample must be random to avoid bias. The sample size of 80 must be under 10% of all purchases to assume independence. And the last condition is that I need to be big enough. Now, how do I know I'm big enough? Well, with proportions, we had 10 successes and 10 fails. With means, we had the central limit theorem that said, as long as you're bigger than 30, you are big enough. Well, with chi-squared, all we have to do is make sure that our expected numbers are all 5 or bigger. So the big enough condition is really the only one that really changes, and it's that the expected counts all have to be 5 or larger. So I'm at 20. So those are all larger than 5, so I'm good to go. All right, so now I need the work. And the work is my favorite part here. So let me get down to the work. The work is finding what I called chi-squared. Now remember, chi-squared, so you take the observed value minus the expected value squared, all divided by the expected. You have to do this for each category, and then you add them all together. That's our symbol for add them all together. So when I come back over here to find my chi-squared, I'm going to grab my calculator here, and I'm just going to kind of start going. So I'm going to use parentheses. It'll make it a little bit faster. So for peppermint, I observed 25 minus expected 20. That number needs to be squared, and then I'm going to divide that by the expected 20. And again, if you do it all at once with parentheses and all that stuff, it'll do it all at once for you and you get your answer, 1.25. And then I have to repeat that process for cinnamon. And then I got to repeat that process for wintergreen. Now, traditionally, you don't have to show all this work, but I do need the final answers, which I will write and down in one moment. I'm just trying to get them all real quick first. And then finally, we have spearmint, observed, minus expected. Now, the observes will always be given to you in a problem. You have to read the problem to figure out what the expecteds are. And that's what I did. I read they were expected to all be equal. And with 80 people, equal would be 20, 20, 20, 20. All right, one more there. So those are my numbers for my chi-squared. And these are what I'm going to need you to write down. So I got 1.25, 0.05, 0.2, and 1.8. And then what I need to do is I need to add them all together. So I'm going to shoot over here for a second because I got to write these down. So my chi-squared numbers were 1.25 plus 0.05 plus 0.2 plus 1.8. And then you could actually grab it. Now, unless you're going to have to do that in your head, adding all these together. But now I'm going to add these all together. And this is going to be, you could call it like your grand total chi-squared. 3.3. It's my grand total chi-squared. So this 3.3 is it's very similar in idea, at least, to a t-score or a z-score, but it's called a chi-squared score. So it's a very different formula, but it's the same kind of idea, right? It's that test statistic that I need. Now I got to calculate my p-value. And watch this. Check this out. Ready? You normally go second vars, and this is where you would get normal CDF if you're trying to find the p-value with a z-score. You get t-CDF if you're trying to find the p-value with a t-score. And if you scroll down to number 8 here, we have chi-squared CDF, and that's what I'm going to use. So I'm going to start at 3.3. That's my value. Now, if you think about it, chi-squareds can only be positive because you're squaring. And when you square numbers, you're always going to be positive. So it's always going to be positive, meaning you're always going to look above. I'm going to go way above, 9, 9, 9. I'm going to go way, way, way above. And now this is where we run into one more little hiccup. What are the degrees of freedom? Most kids are going to say, oh, I remember degrees of freedom, sample size -1. Well, that's when you're working with means. When you're working with chi-squared, it's how many categories do you have -1. So I had 4 categories of gum. 4 minus 1 is 3 degrees of freedom. So it actually has nothing to do with your sample size. It's about how many categories do you have -1. So similar formula, yet a little bit different. So you got to remember that. That's one thing you do need to kind of pay attention to and study. And this will simply give me my p-value of 0.3476. Oh, you know what? That's getting awfully messy here. I should be writing a p-value, sorry. So the p-value is 0.3476. Now remember, a p-value is the probability of your sample occurring, assuming the null is true. So assuming that there is no difference and that they're all equal, 20, 20, 20, then the probability of seeing the numbers I saw would be, well, pretty likely. And remember, what that means is I'm going to fail to reject the null. I'm seeing something happen that's really not that big of a deal. And if you look at the numbers, you kind of can get that idea. 25 is not that different. 19 is certainly not that different. 22, 14, they're just not that different. So now this leads me to my fourth step, and that is my conclusion. And I will say, since my p-value is less than, boy, having one of those days, not less than, it's more than, since my p-value is more than, and then you could use any alpha you want. Typically we'll use a 5% alpha level, so since my p-value is more than 0.05, I will fail to reject the null. There is no evidence of an unequal distribution of flavors. I mean, I am seeing a difference, but it's just not significant enough for me to officially say, oh my goodness, the flavors are not equal. Well, I mean, yeah, they're not equal, but that doesn't mean they're not equal, right? Just because a sample's a little bit off from what's expected doesn't necessarily mean anything. So that's the process, right? You don't have to draw fancy pictures, actually less symbols than there are for z-scores or t-scores. It's really all about understanding observed and expected, calculating that new test statistics of chi-squared, and then finding your p-value using the new chi-squared CDFs. It's actually a pretty fun process. Let's look at one more problem here. So in this example, a grocery store in a large city gets customers from all over the city. Typically gets 40% of its customers from the north, 20% of customers from the south of the city, 15% from the west, and 25% from the east. A recent sample of 650 customers was asked what part of the city they were from, and here are the results. So the recent sample showed 221 from the north, 125 from the south, 138 from the west, and 166 from the east. Conduct a test to see if the distribution from the city has changed. So again, the question is going to help you with the null and the alternative, right? So the alternative is what we're wondering. Has it changed? So the distribution, oh boy, I'm having a really hard time today, spelling and everything. The distribution of customers has changed. And the null would be that, nope, it hasn't. Everything's the way it should be. The distribution of customers has not changed. Or you could even say is the same. That might be a better way of saying it. And then the alternative would be it's not the same, which means it's changed. So you can word it a little bit differently and you're still going to get it right. All right, let's check those conditions. The sample must be random to avoid bias. It did say as a recent sample. You assume it's going to be random to avoid bias. 650 customers. That's a lot of customers, but I'm assuming a large grocery store is going to have a lot of customers. So 650 could be assumed to be under 10% of all customers. And finally, we do have to check our expected numbers, right? So that's what I'm going to add into the chart here. So how do I get those expected numbers? Well, I need counts. I don't need percentages. I know 40% are supposed to be from the north. So if I take 650 times 40% or times 0.4, there were supposed to be 260 customers from the north. The south was 20%, so 650 times 20% is 130. There were supposed to be 130 from the south. The west was 15%, so 650 times 15%. There was supposed to be 97.5 of customers from the west. That was expected. And the east was 25%, so 650 times 0.25 is 162.5. So if I look at these numbers, the north looks a little bit off, south looks pretty good, east looks pretty good, and the west looks a little bit off. But again, just because I see something different doesn't mean there is a difference, and that's why we're conducting the test. So the other condition I need to check is that all of my expected values are 5 or larger. All right, so now that I have that, doing the actual chi-squared is easy. Remember, it's just a formula. So for the north, 221 minus 260 squared divided by the expected 260. And then I'm just going to repeat this process. The south, I observed 125. I expected 130 squared divided by the expected. And for the west, I observed 138 minus I expected 97.5 squared divided by the expected. And for the east, I observed 166 minus 162.5 squared divided by 162.5, the expected. All right, so I just got to write down all these numbers. Again, these are what I need, 0.075 and 16.82. And again, I typically write them down as I go, 0.19 and 5.85. All right, so now I got to add all those together to get my grand total chi-squared here. So 0.075 plus 16.82 plus 0.19 plus 5.85. So I get my grand total chi-squared 22.935. 22 and I forget it already, 0.935. All right, so it is important. You don't have to show all of that work. I mean, you're doing the work on the calculator, but you do need to write down your numbers. You do need to write down all the individual chi-squareds. So that was 0.075, and again, the order doesn't really matter as long as you get them all there. 16.82, 0.19, and 5.85. Now, the smaller the chi-squared, that means your observed and your expecteds were pretty close. The bigger the chi-squareds means that they're kind of far away. And now I just need my p-value, and that'll help me make my conclusion. So, I mean, I hope you guys are like, wow, this is pretty easy. Yeah, these chi-squared problems are actually really fast and painless. You just got to know what to do, obviously. So I'm going to grab chi-squared CDF. I'm going to start at 22.935. I'm going to go way up because the only direction you could go in a chi-squared test is up. And how many degrees of freedom is? Well, I had 4 different locations, north, south, east, west. -1 is 3 degrees of freedom. So it's always categories -1. And that gives me a p-value of, whoa, look how low that p-value is. That's 0.00042. 0.00042. So with that, I will reject the null. And what rejecting the null means is I'm going to have evidence. So I do have evidence to go with the alternative. So I do have evidence that the distribution of customers at the store has changed. And keep in mind that, don't get tricked. Yes, the north and the west, the north and the west were the ones that were off. The south and the east, they were pretty close. But if one category is way off, then the distributions we thought were true are obviously not true. So, quick rundown of chi-squared. Categorical counted data across many categories. Make sure you understand the process of a test is the same with our 4 steps, but the big difference comes in the chi-squared, creating the chi-squared, which is, again, pretty easy. So, try out the practice problems that are in this, in the assignment as well. Hopefully this video helps explain it all to you. And, chi-squared most kids end up liking. It's really not that much work. All right, enjoy.